Hello everyone, welcome back to the channel. This is the continuation of our previous lecture on the Legendre Differential Equation, which we solved using the power series method. In the previous lecture, we assumed a power series solution and obtained the recursion relation for the coefficients. We will study the recursion relation separately for even and odd values of j. From this, we will obtain two independent series solution and we call them as even power series and odd power series. Without making any delay, let's continue our derivation from the recursion relation obtained in the previous lecture. We had stopped at recursion relation aj plus 2 is equal to minus of L minus j into j plus L plus 1 divided by j plus 2 into j plus 1 into aj. This was the recursion relation that we had stopped at. Now, from this recursion relation, we are going to put the values for this j. Now, once we are substituting the values for this j, I am going to get the different coefficients depending on the values of j. Now, the j can be, as I said in the earlier, j can have even or odd values, right? So, even values and odd values separately, they are going to provide us the even power series and odd power series. So, since those power series which we are getting depending on the value of j, we are going to obtain it from this recursion relation. So, let us start with that substitution for j value. Now, let us write it. Substitute for j values to get coefficients. Now first let us consider even values of j. Okay, so for even values of j, I'm talking about the values 0, 2, 4, 6 and so on. Now we are going to use these j values and get the coefficients here. Okay, so let us consider the first j value, that is j is equal to 0. Now first value from j is equal to 0, I can get the coefficient as a2, right? So a2 will be, just substitute the values of j is equal to 0 in recursion relation, that is minus into L into L plus 1 whole divided by 2 into 1 into a naught. Remember, this a naught we had considered it as arbitrary value. So a naught is not equal to 0. We had considered it in the solution, right? So when we had assumed y of x as a solution, there we had considered that this a naught cannot be 0. Right? So just look at this. If a naught is becoming 0, the coefficient a2 will also become 0. Since I'm getting a2 value in terms of a naught, so this a naught, if it is not equal to 0, I'll get a2 value. If a naught is becoming 0, then I'm not getting any a2 value for it. Right? Since we had assumed that the y of x is a power series solution and we had put the condition that a naught is not becoming 0, so hence a2 exists here. right? So let us check back for the next value of j. Now next even values of j is equal to 2. Now substitute the value of j is equal to 2 here. So what will be j is equal to 2? My recursion relation will be a4, right? a4 is equal to minus into L minus 2 into L plus 3 into A2 the whole divided by 4 into 3. Now since I know the value of A2, let me substitute the value of A2 there, that is minus into L minus 2 into L plus 3 into A2 value is minus L into L plus 1 into A naught the whole divided by 4 into 3 into 2 into 1. Simplify this. Don't multiply. Simply keep all those things as it is since we are generalizing the things. Minus 1 raised to 2 into L minus 2 into L plus 1 into L plus 3 the whole divided by 4 factorial. Can I say that 4 factorial? 4 into 3 into 2 into 1 into A naught. Now my A4 is also I am getting it in terms of A naught. Right? So if A naught is existing, A4 will also be existing. So similarly, for the next value of j, that is j is equal to 4. I'll get the coefficient as A6. Now what will be A6 when I put j value as 4? Minus into L into nothing but L minus 4 I'm getting into L plus 5 I'm getting divided by 6 into 5 into A4. Yes, like that. So it is again you have the value of A4. Substitute that as well and write it. So it would be minus 1 raised to 3 L into L minus 2 into L minus 4 into L plus 1 into L plus 3. The value of is L plus 5, right? Into A naught the whole divided by 6 into 5 into 4 into 3 into 2 into 1 is 6 factorial, right? So this will be my A6. Now just look at the trend that is going. So A2, in A2 we had minus 1 raised to 1. In A4 we had minus 1 raised to 2. Right? So in A6 I'm having minus 1 raised to 3. Now just take the next value of j here. J is equal to 6. My coefficient would be A8. Right? Now A8, looking at this trend, tell me what will be the value of A8. A8 would be minus 1 raised to 4 into, if nothing is present, L minus 0 will be my first term here. L minus 2, L minus 4 will be for A6. Now what will be for A8? It is L into L minus 2, L minus 4 into L minus 6. Yeah, again for the next terms, it will be L plus 1 into L plus 3, L plus 5, L plus 7 into A naught divided by, look at this, for A6 you have 6 factorial, for A8 you will get 8 factorial. Like this, different even values of j, you are going to get the different coefficient depending on this value of j. So in general, I can write as, in general, for even values of j, I can write as, look at this, what will be my coefficient, general coefficient for even values of j. Look at this, 2 into 1 for j is equal to 0. For j is equal to 2, you had a4, right? So for a4, I can write 4 as 2 into 2. Similarly, a6, I can write 2 into 3. For a8, I can write 2 into 4. So in general, my general coefficient for even values, can I write it as a to r, where r is 1, 2, 3, 4, right? So on up to n. So I can write the general coefficient as a to r equal to minus 1 raised to 4 for a8 when r value is 4. So a6, 2 3s are 6, where minus 1 raised to 3. So this r is similar here. So I can write as minus 1 raised to r L into L minus 2 L minus 4, like that, up till for my rth term. So rth term, can I write it as L minus 2r plus 2 by looking at this trend? Yes. And for this, I can write it as L plus 1, L plus 3, so on up to rth term. I may get it as L plus 2r minus 1. Yes. Of my E naught. A naught is common in every term. Right. Now the whole divided by factorial term I should mention. Right. So for factorial term, since it is a8 8 factorial, a6 6 factorial, same way for a to r, you will get 2r factorial. 2r factorial. So this is the recursion relation. This is the recursion relation for the even values of j. Okay, so this is the recursion relation. So let me consider this equation as equation 7. On continuing with the previous lecture, let me consider this equation as 7. So recursion relation, this equation was equation 6. So we will consider this as equation 7. Now this recursion relation, we call it as even power series. Right? Now for odd values of j, right? So for odd values of j, I'm talking about the values 1, 3, 5, 7, so on. Right? So again from the recursion relation. The recursion relation, I'm talking about the equation 6. Right? So recursion relation was aj plus 2 is equal to minus L minus j into j plus L plus 1 divided by j plus 2 j plus 1 into aj. So here, now from this 6, now the first value of j as odd is 1. I'll get the coefficient as A3, that is equal to minus into L minus 1 into L plus 2 whole divided by 3 into 2 into A1. Now look at this value A1. Now we had considered when we were solving about the value of k, right? When we were discussing about the value of k from the indicial equation, we had chosen this value of A1 as arbitrary value, right? So from the indicial equation, we had got the two values of k is equal to 0 and k is equal to 1. So for k is equal to 0, A1 was arbitrary. For k is equal to 1, we had A1 becoming 0. So since A1 is becoming 0 for the value of k equal to 1, we had not chosen the value of k as 1. Instead, we chosen the value of k as 0. Why? Because A1 is becoming arbitrary, right? So if A1 is becoming arbitrary, I can take the value of A3. Meaning is A3 can exist. If I choose the next value of j as j is equal to 3, I will get the coefficient as A5. Now A5, I can calculate it as minus into L minus 3 into L plus 4 divided by 5 into 4. Substitute that. So A3 I have the value as L minus 1 into L plus 2 whole divided by, I had 3, 2 into 1 in terms of A1, right? On combining, I can write A5 as minus 1 the whole square into L minus 3 into L plus 4 into L minus 1 into L plus 2 whole divided by, I can write it as 5 factorial into A1. Similarly, when I take the value of j as j is equal to 5, next value of the j, I can write it for A7. Now A7 would be, look at the trend and tell me, it is minus 1 the whole cube L minus 1, L minus 3, L minus 5 into L plus 2, L plus 4 and L plus 6 into A1. The whole divided by 7 factorial, right? So in general, I can write it as, in general, I can write the power series for odd values of j as, do you want me to write it for A8? A8 you had it in power series, even power series. Okay, so you'll get A9 in the next. Okay, all right. So for A3, can I not write it as AR plus 1? Shall I write it as AR plus 1? Look at this. If R is becoming 1, first value of R becomes 1, you'll get A3. If R becomes 2, you'll get A5. 2 3s are 6 plus 1. Right? So in general, I can write the term as coefficient A to R plus 1. This is nothing but minus 1 raised to, look at this, A7 you have minus 1 raised to 3. For A5 you have minus 1 raised to 2. So like that, for a to r plus 1, you will have minus 1 raised to r into l minus 1, l, l minus 3 into l minus 5 into l minus 7, so on up to l minus 2r plus 1. L minus 2r plus 1. Again, this is L minus 2r plus 1 is for the first negative terms what we were getting, right? Similarly, for the next trend, that is L plus 2, L plus 4, like that till up till L plus 2r into A1. Now the whole thing divided by, look at this, 7 factorial. Same way for a to r1, a to r plus 1, you will get 2r plus 1 the factorial. This is the general coefficient for the odd values of j. Okay, on combining, let me take this equation as some equation. We had stopped at 7, so let me take it as equation 8. These are the coefficient of the solution that we had considered earlier. We had considered solution as y of x is equal to summation n is equal to 0 to infinity a n x raised to k plus n, right? Where a naught is not equal to 0 we had considered as a solution, assumed solution I am talking about, right? Now here y of x is nothing but, now what is this summation is indicating? All those coefficients, right? So here we have, from the initial equation we got to know that this value of k is 0. If k is becoming 0, meaning is a1 is not equal to 0. If a naught is not equal to 0, I am getting even power series. If a1 is not equal to 0, I am getting odd power series existing. So same way, general solution for the Legendre differential equation combining the even and odd power series is, it is a naught a1 plus for a2 you had written it in terms of a naught, alright. So nothing but a2, a3, all those things along with what, x raised to 0, x raised to 1, x raised to 2, x raised to 3, like that up till all those infinite terms, right? So this thing we are writing it as what, a naught into x raised to 0 plus a1 x raised to 1 plus for a2 we had found it even power series. So even power series is nothing, it is in terms of a naught, right? So here we are getting even power series and odd power series. So a naught and even power series, I can group them into one. A1 x raised to 1 and odd power series I can group into another and write it combined solution as y of x is equal to a naught into 1 plus summation of all the terms from r is equal to 1 to infinity. I can write the even power series as minus 1 in raised to r, l into l minus 2, l minus 4, so on up to the rth term for this series, that is l minus 2r plus 2 into l plus 1, l plus 3, so on up to l plus 2r minus 1 raised to x raised to 2r. The whole thing is divided by 2r factorial, right? So this is my even power series plus x into a1 again x into a1 I can take it in common, that is 1 plus summation r is equal to 1 to infinity minus 1 raised to r, this odd power series I am writing, okay, to L minus 1, L minus 3, so on up to L minus 2r plus 1 into again the next L plus 2, L plus 4, so on up to L plus 2r into x raised to 2r. The whole thing divided by 2r plus 1 factorial. Now this is the assumed solution that we have considered as a solution to the Legendre differential equation. Right? Now let me take this equation as equation 9. Yes. Now this 9 is the sum of even power series and odd power series. Right? So this we assume, what we had assumed that y of x in terms of a n x raised to k plus n as my assumed solution, where that is satisfying the Legendre differential equation. Now in terms of the power series, in terms of the even power series and odd power series, we had found that value of y of x, which is the solution to the Legendre differential equation. So we can say that the assumed solution is a solution to Legendre differential equation. Why? Because it satisfies the Legendre differential equation. This summation is up till infinity. I am getting the terms here. I may get the even power series and odd power series. But we need a finite series as a solution to the Legendre differential equation, right? So what we are going to do, we are going to take the descending powers of x and write a very single finite series, and we treat that series as a solution to the Legendre differential equation. So let us consider the descending power of x, powers of x. Now for that, what we are going to do, we are just going to modify this recursion relation. Look at this recursion relation. So we had the recursion relation. Let me take this only. Okay. So here we had this equation 6 giving me the recursion relation where aj plus 2 we were getting it in terms of aj, right? So here every coefficient I am getting in terms of j. In the increasing values of j, I am getting this all coefficients which I may get it for all those infinite terms. But since we are finding it in terms of the descending powers of x, what we are going to do, we are just going to modify that recursion relation. Now how we are going to modify it? Just to look at this, I had aj plus 2 something in terms of aj, right, as a recursion relation. Now what I'll do, I'll just take this everything, I'll send it to the other side and write this aj. Now what is my aj is? Aj is equal to, look at that, it is minus j plus 2 into j plus 1 the whole divided by L minus j into L plus j plus 1 into aj plus 2. Right? Now, just by making some alteration with the recursion relation, I'm getting a new recursion relation, right? And this is the recursion relation, naming the equation as equation 10, right? Now equation 10 will give me the descending powers of x. Now the coefficients for the descending powers of x, this equation 10 is going to give it to me. Let me take, this is the recursion relation for descending powers of x. Okay, so this descending powers of x will give me the single finite series. Okay, that we are going to get it now. The single finite series in descending powers of x. Of x. Now, in order to have this descending powers of x, I'll go on changing the values of g. Then I'll get a general series, and that general series is my finite series. Okay. Now here, to have that finite series, meaning is we are combining the even power series and odd power series into one finite series. Okay, so for that what I'll do, I'll put the values of j as j is equal to L minus 2. Now if I substitute the value of L minus 2, what will be my coefficient? Put the value of L minus 2 in 10, in equation 10. So I'll get the general coefficient as AL minus 2 is equal to minus of L minus 2 plus 2 would be L, yes, into J plus 1 is L minus 1 whole divided by 2 into 2L minus 1 into AL, right? Again, for the next value of J, what I'll do, I'll substitute the value of J as L minus 4. Again, new coefficient would be A L minus 4. This will give me what? L minus 4 will be minus 1 into L minus 2 into L minus 3 whole divided by 4 into 2L minus 3 into AL minus 2. I know the value of AL minus 2. Substitute back the value of L minus 2. I will get the AL minus 4 as minus 1 raised to 2 into L into L minus 1, L minus 2 into L minus 3 whole divided by 2 into 4 into 2L minus 1 into 2L minus 3 into AL. Look at this. You are getting AL minus 2 in terms of AL. AL minus 4 in terms of AL. Right? So AL is my arbitrary value. Okay. So in general, now let me take another value also. J value as L minus 6. So what will be my coefficient? Coefficient would be AL minus 6. Look at the trend. Minus 1 raised to 3. L into L minus 1. L minus 2. Next term L minus 3. into L minus 4 into L minus 5 whole thing divided by 2 into 4 into 6 into 2L minus 1 to L minus 3 into 2L minus 5 whole thing into a L. Right? So in general, I can write the general coefficient, right, as, look at that, L minus 6, L minus 4, L minus 2. Can I write it as AL minus 2R as my coefficient? Yes. L minus 2 3s are 6. L minus 2 2s are. L minus 2 1s are. Right? Like that. L minus 2R. So minus 1 raised to R into L minus 1, L minus 2, so on up to L minus 2R plus 1 into AL. The whole thing divided by, look at this, 2, 4, 6 and all. So I'll get 2, 4 into 6, so on up to 2R. Yeah. For the next, that is 2L minus 1. 2L minus 3, so on up to 2L minus 2R plus 1. Yeah, so this is my general thing. But this is not giving me again. This is still rth term. Somewhere from infinity we had reducing it to a descending powers of x. So somewhere it is going to give me 3, 2 into 1. Right? But 3, 2 into 1, I'm not getting it till this. I'm somewhere landing at R. From infinity, I'm somewhere landing at R, but I need to factorize this. I need to make a simplification from this R to getting 1, 3 to 1. This descending will give me that solution of Legendre differential equation. I am having the odd power series, even power series from 0 to infinity, but here in this general solution coefficient, I am somewhere landing at R. From this R, I am going to I should land at 3, 2, 1, getting a factorials, right? So for that, what I'm going to do, I'm going to check for all those denominator and numerator terms and check how this landing is giving me the factorial, how that landing is giving me the finite solution to me, right? So just look at this value. You have L into L minus 1, L minus 2 and so on up till L minus 2 R plus 1 till rth term. So let me consider that L into L minus 1, L minus 2, so on up to L minus 2 R plus 1, right? So can I write this as L into L minus 1, L minus 2 into, so on up to L minus 2R plus 1 into, I'll just multiply and divide L minus 2R factorial. I'll multiply and divide it by L minus 2R factorial. Did I make any change? Look at this above numerator term. L minus 1, L minus 2 up till L minus 2R plus 1. Again minus 1 will give me L minus 2R factorial. This is L minus 2R minus 1. L minus 2R minus 2, L minus 2R minus 3 till the terms 3, 2, 1. Yes. So nothing but I can get that numerator term as L factorial divided by L minus 2R factorial. The whole thing, this, I can write it as L factorial divided by L minus R factorial. Okay. So again, check back the next term, that is 2, 4, 6, right? So let us consider that 2, 4, 6 now. Now here I have 2, 4, 6 into 2r, right? So nothing but what? I can write this as 2 into 1, 2 into 2, 2 into 3, up till 2 into r. So how many times I'm getting 2 in every term? 2 raised to r times, right? So I can write this the whole thing as 2 raised to r into r factorial. Yes, I can write this 2, 4, 6 up till 2r as 2 raised to r into r factorial. Now again you have the other term, that is this 2l minus 1, 2l minus 3 up till 2l minus 2r plus 1. So how can I write that now? Yes, just look at that. You have 2l minus 1, 2l minus 3, you have 2l minus 5. So this thing, it is till 2l 2r plus 1 till this term. Now again simply what I'll do, I'll just multiply and divide it by 2l minus 2r factorial, because that is the missing terms here, right? So it is 2l minus 2r factorial. Now if I am doing this, right, this is giving me 2l minus 2r factorial, but there are some other terms also which are missing, which you can write here. Now what is that thing? It is nothing but just multiply all those even terms and divide it by the same. Yeah, because this won't give you the finite series. So what I'll do, I'll just multiply and divide it by even values, even terms here. Just look at that, how it is going to change, right? So it is nothing but what? I'm getting 2l factorial here. Yes, how? 2l minus 1. Why? Because these are missing here, right? This is odd values, 2l minus 1, 2l minus 3, 2l minus 5 up till this. These even values here, they are missing, right? What I'll do, I'll just divide them and multiply them to get 2l factorial. Here I'll get all those even terms in the denominator. That thing we are going to do it here. Okay, so it is nothing but 2l into 2l minus 1, 2l minus 2 up till 2l minus 2r plus 1 into 2l minus 2r factorial whole divided by all those even terms that those are missing. 2l, 2l minus 2, 2l minus 4 up till 2l minus 2r plus 2 into 2l minus 2r factorial. Now simply I can write this as 2l factorial into 2 factorial into l minus r factorial. The whole divided by, I can write 2 raised to r into 2 into whole thing, taking out 2 in common all these in all these terms. It is l into l minus 1, l minus 2, so on up to l minus r plus 1 into l minus, to be specific, it is 2l minus 2r factorial. Now on simplifying, I can write the whole thing as 2l factorial divided by l minus r factorial divided by 2 raised to r into l factorial into 2l minus 2r factorial. Now central coefficient, now I can replace it as L minus 2r is equal to minus 1 raised to r L factorial. Substitute all those alterations what we have done. So a 2 raised to r into L factorial into 2L minus 2r factorial, which is in the denominator here. Okay, that thing will come in the numerator term, divided by 2 raised to r into r factorial, that 246 what we had done this term. Okay, into L minus 2r factorial into 2L factorial into L minus r factorial, the whole thing multiplied with AL value. And rewrite this substituting this value of AL, right? Now it is a standard value. Consider AL, or you can write choose. Now choose AL value as 2 raised to L factorial divided by 2 raised to L into L factorial the whole square. Now if I am choosing the value of AL as this, meaning is I am substituting the value of AL as this, right? On substituting the value of AL, I'll get the coefficient in terms of L factorials, R factorials, 2's and all, right? Now I can write simply y of x, my solution, as summation r is equal to 0 to some n value, because it is a finite series, minus 1 raised to r into 2L minus 2r factorial, right? The whole divided by r factorial into L minus r factorial into L minus 2r factorial into 2 raised to L. Now this is the coefficient into x raised to L minus 2r, where n value will be L minus L by 2 for all n becoming even values, right? And L minus 1 by 2 is the n value if L is becoming the odd value. Now this is y of x. Now this y of x is PL of x, meaning is we say that this y of x is nothing but PL of x. We call it as the Legendre polynomial. PL of x is the solution to the Legendre differential equation. So PL of x, nothing but y of x, we had assumed it as a descending power of x and found the value of y of x, found the solution to the Legendre differential equation in terms of L and R. Now that is Legendre polynomial. PL of x is naturally the solution to the Legendre differential equation. So in the next lecture we will study the important properties of this Legendre polynomial, which is having the most important role in the mathematical physics as a special function in mathematical physics. So thank you for watching. If you found this lecture helpful, please like, share and subscribe to the channel. Thank you.